Okay, antenna simulation overview is the title of my talk, as mentioned. My name is Mark Richlin. I think if you've been a CST user and attended our events in the past, you'll probably have seen me speaking before about antennas or microwave components. That's my background. And I've been with Dassault System, CST, before that for the past 13 years in various roles. But as I was saying, so simulation is intended to help engineers confront the challenges they are faced with. Those challenges are not necessarily of our making as engineers, but they are of our making as consumers. We may need new technology, not in 10 years' time, but tomorrow. As a consequence, what we now have is very short design cycles, perhaps of the order of months in some cases. So there's very little time to iterate and to test new prototypes. We also have a large number of product variations. I don't particularly like Tillman's mobile phone. I want one that is different, perhaps of the same manufacturer, but a different brand. We all have our own tastes, and the product variations are intended to suit all those different tastes. Finally, we expect devices to have more and more functionality. So standalone digital cameras or music players are pretty much niche items nowadays. We want integration. Everything has to fit into this one package, whether you're talking about a phone or a car or an airplane module. That results in unwanted interactions, or can do, and interference between those systems, which have to be understood and resolved. And those are the challenges that simulation tools today must help the engineer to face. To be used effectively, though, simulation has to be used at all stages of the design process, and particularly importantly, it has to be used as early as possible. Why early? Well, the earlier you can use it, the more quickly you can identify possible issues, and the more time and options you have to resolve those issues. Getting a robust working design early on reduces the overall risk and cost for the project and avoids delays for the whole product development cycle. So simulation is really crucial if you're to achieve this goal. But let's talk a bit about antennas. First of all, we're designing antennas with a particular purpose and environment in mind. And those lead us to specifications. We have to start with specifications, which could be qualitative or could be quantitative. So qualitative being, it mustn't be too heavy, it mustn't be too expensive, it should allow flexible usage, whatever that means, but qualitative as well. So we need a frequency range and a polarization. We need scanning characteristics and a whole bunch of other numbers that we have to assign to the antenna performance at the end of the day. Those then allow us to do some kind of antenna design, to certify that design, and then finally, once we have success, hopefully, we report those results, and the antenna can be used in the product that it was designed for. Of course, if we don't have success, it's still useful because we report the results back and inform modifications perhaps to the specifications that were put in place originally. Now, where does simulation fit in? Well, simulation fits in particularly importantly at the two middle, most time-consuming stages, at the design and certification stages, but actually it can be used at an early stage to inform the design of the specifications themselves. And of course, simulation results are used extensively in reporting and also perhaps in marketing activities. So you could say that simulation underpins the entire antenna design process. The structure of my introduction, I've kind of divided it up into 4 stages. So first of all, I'd like to talk about simulation techniques, then how those simulation techniques apply to simulation. When do we use what type of tool for what sort of application? Looking at antennas in their environment, a very important aspect and a challenging aspect of simulation. And finally, looking at how simulation supports the certification in terms of both safety, but also in terms of electromagnetic compatibility of antennas. I won't be talking about electromagnetic compatibility so much today, but certainly the safety aspects. So let's start with simulation techniques. An efficient analysis of an antenna depends on what type of antenna you're simulating and how it behaves. Okay? When I say efficient, I mean getting to a correct or an accurate result, a usable result in the real world in as short amount of time as possible. And that depends very much on whether your antenna is large or small, whether it contains tiny geometric features, whether it's a wideband antenna or a narrowband, multiband perhaps antenna that is extremely resonant. So for example, if we look at more wideband type antennas, whether they're large or they're small, a time domain approach might be applicable. So we've maybe heard of FDTD numerical methods. We have in CST Studio Suite, we have the FIT method, finite integration technique, and the TLM method. If we're looking at smaller, more resonant, in particular, more resonant antennas, and actually they're becoming increasingly large nowadays with what we can solve, we might think of a frequency domain approach. So the FEM, finite element method, or some kind of model order reduction based variant of that. If we go larger in terms of geometry, then we might think about using surface mesh-based approaches like the integral equation technique, so method of moments, or multi-level fast multipole methods, or even larger, especially when we're thinking about antenna placement, we might be thinking of asymptotic techniques like the shooting bouncing ray method. Now, all of these results, with the exception of the asymptotic approach, will be able to get you a result for your antenna. All of them support hardware acceleration like GPU acceleration, MPI acceleration, domain decomposition, multi-core simulation, and so on. It's just about choosing the right one to get you to your result as quickly and as accurately as possible. So if we look at the range of solvers that we have, we can distinguish them basically between ones that use a volumetric mesh and ones that use a surface mesh. So volumetric mesh-based approaches are the time and frequency domain. Those are particularly useful when you have